Right, it's bang on 2 o'clock, so we will get started still as people coming into the lobby will admit them. So welcome to the inaugural webinar of AIchemy. I'm going to keep it very, very short, just because we have two great talks and we only have 1 hour. So if you have any questions during the talks, please do use the Q&A and pop them in there. And if you like that question, please do thumbs it up and I'll try and prioritize those when we do the questions at the end. So with that, our first speaker is Annabel Basford, who is in Professor Kim Jelf's group, co-supervised by myself. We'll stop sharing screen so you can share your slides, Annabel.
Yeah, thank you for the introduction, Becky. I'm going to talk about streamlining the automated discovery of porous organic cages. So these are a subclass of supramolecular assemblies. They're often used as porous materials, and they're made through dynamic covalent chemistry, which is the reversible formation of covalent bonds. They are discrete cavities, they've got accessible windows, and they're solution processable, which gives them a whole range of different applications in host gas chem, gas storage, separations, and even as porous liquids. We might describe them by their topologies. So here we can say a tri-4-di-6 or a 4+6 cage, where we have 4 of the tritopic precursors and 6 of the ditopic precursors assembling into this higher order structure. So yeah, dynamic covalent chemistry, or DCC, it's great. We benefit from like an error correction mechanism where reactions can really drive and go to full 100% conversion. But we can see even from the schematic, from simple building blocks, we might get a whole range of different type of outcomes that might occur. And we might attribute this to internal factors such as precursor design or external factors such as reaction conditions. So yeah, again, looking at our tri and ditopic precursors, we might make a cage, which we're targeting, but we can see other type of structures that we might get instead. Again, we look and target a certain size or topology, but we might see other topologies forming, or these topologies might even interlock and form catenanes. And then we have our DCC reaction, so we can get a full conversion into what we think the cage is the thermodynamic product, but we might see these cage intermediates on the way. And then finally, we've got the cage, it's the target topology, it's gone to full conversion, but whether it actually is shape persistent or it might still collapse in on itself into a higher density structure, we do not know. So all of these different factors make the design and targeting of these materials particularly difficult. So instead of relying on trial and error and serendipitous discovery, what my PhD has entailed has been combining high throughput screening, robotic automation, and computational modeling into a streamlined workflow. So, yep, we did the synthesis and characterization in high throughput experimental workflow, did some computational modeling to do our property prediction of these cages, and then to address one of the biggest bottlenecks so far is we created an automated data analysis workflow to streamline that, because very essential. So first up, what we did was create a precursor library of tritopic and ditopic aldehydes and amines. We used an OpenTrons platform, which some of you might have used. It's a liquid handling platform. It's really cheap. It's only about 5K. It's got a wonderful open source API, so it's really easy to use and totally customizable. And we did this for both the synthesis and all the sample prep for characterization. Next up, we've done all our reactions. So we had our precursor library, we had all our combinations, but we want to work out what's going on. So to work out our species type, we actually use computer vision, namely the Hindsight package from Jason Hines' group in Vancouver. And what we did was utilize one of the good properties of cages about them being solution processable, whereas they should dissolve in common organic solvents. So we take our blank solvent as our reference versus our sample we measure. If it's dissolved or close to the reference, we shouldn't see any precipitate, and therefore it is dissolved and molecular, whereas vice versa, if we see precipitate forming, it's probably going to be a polymer or an oligomer. And what we further streamlined this with was integrating a Dobot MG40 robotic arm. And this was really great because before, myself and the master's student would have to load up each file individually and it'd be really long. But integrating this further streamlines this whole process. Then we want to think about conversion. So we used aldehydes and amines to make imine porous organic cages. So we wanted to scan two regions of our NMR spectrum. So we wanted to look for a yes for peaks in the imine region, but because we use an excess of, say, amines over aldehydes, we assume that the amine can fully consume all the aldehyde, and therefore we shouldn't have any peaks in the aldehyde range, and therefore that's a tick. And we streamlined this by using the Python package NMR glue, which is all open source. Then to finally assess the cage size or topology, we scan the mass spectrum for the 4 most common types of cage topologies for this type of combination, and streamline this with NZMine and PyOpenMS, 2 again open source packages. And then finally, we integrated the computational side. So we read in all our precursor building blocks as smile strings, assembled them using our supramolecular toolkit, which is again a open source package free to use to create our cages, conducted quick MD lowest energy conformer searches, and then created our cages of what we think they should look like, and used PyWindow to assess whether they were shape persistent or they had collapsed. So we have all this data that fully characterizes direction outcome, but we want to put it all in one machine readable data frame. So what we did was create a SQL-based cage database tool, appropriately named cagey, and again, all open source. So this does the file conversion or the analysis and the concatenation of all the different data into one streamlined workflow. We can track every experiment by its plate and its formulation number, so position in the plate, and then we can look at combining everything that way. So even from one screen conducted under one set of conditions, we can see how our precursor combinations can flow towards, is it turbid or is it clear, what the conversion is, and then the topological outcome as well. What we might want to target ideally is the clean formation of a single cage topology, because therefore this would require the least amount of post-processing because we've got our caging and it's pure, ideal. So what this might look like is, say we have blue is pass and yellow is fail. We want to pass our species type, we want to pass our conversion, and we find one cage topology. And looking at this Sankey plot, we can see 54 cages or precursor combinations with this outcome, and we can see what these cages might actually look like from our computational models. Furthering this, even from a researcher, you think, okay, there's still accessible structures that even require only one step of purification. So using the example below, we can see that in this case, this precursor combination resulted in full conversion via NMR. We saw a single cage topology, but we did see some insoluble precipitate. So this means we might have formed both cage and polymer, but that's okay, because even if we do one simple purification step, then we can still access all these cages. So that's great. We can have a whole range of other cages that we might access that still might be desirable to a researcher that we haven't spent a long time trying to analyze all this data to get there. So now we can start picking out different precursors trends, so we can elucidate our structure property relationships and assess what our internal factors are on the outcome of the reactions. And when we allocate a label to both our tritopic and ditopic precursors as either flexible or rigid, or various combinations of all, if we look at cases where cages cleanly formed, so all blue, past everything, we can see that a rigid tritopic precursor and a flexible ditopic precursor resulted in the most amount of this outcome. Whereas the least amount was a rigid precursor. And if we look at the opposite, so outcome where no cage topology was found, especially via mass spec, we can see that the highest proportion of this was actually a rigid combination. So we think, okay, rigid precursors, they might be good at introducing pre-organization or directionality to the bonding, but if we have too much rigidity, this actually might lead to geometric mismatch, and this might lead to insoluble polymers forming. So we can already elucidate what we might want to target when thinking about future precursor pairs to target materials. Then we were like, okay, so what causes rigidity? Maybe it could be linked to the number of aromatic rings in our precursor pairs. So we sum that up. And again, we can see a nice trend coming out where 1 to 4 aromatic rings is ideal for clean cage formation, but it really drops off when you get 5 or 6. Whereas with the cases where no cage topology was found, we see a steady state where higher number of aromatic rings result in the no cage topology forming. So now we can think, okay, too much rigidity can come from too many aromatic rings, and therefore we can adapt this to further tailor cases where we want clean formation. What we also wanted to do is link in our computational and experimental results together. So in these histograms, we can see the 4 most common cage topologies that we modeled. And we wanted to look at the computationally observed ones. So these are shape persistent. So they have the internal cavity and the correct number of accessible windows. And overlaid for each topology in the hatched boxes of the histogram are the ones we experimentally observed. And we can see that there is a big gap between the ones we experimentally observed and the largest ones we predicted computationally to be shape persistent. So maybe we're not accessing these larger, more poor structures because we're still only conducting this workflow under one set of conditions, i.e. we're not accessing our chemical space enough. But in the future, by means this automated workflow can be adapted for this screening of external factors as well as internal factors. Then what we thought, okay, we don't want to just do this for one type of material. So we moved on from porous organic cages to metal organic cages. So again, we used our amines and our aldehydes, but these created ligands, which can self-assemble with metal ions. And we can screen against different counter ions to create our automated synthesis workflow. We can then automate our characterization analysis again. We can identify hits of this workflow. And then what we did, we actually scaled up some of the hits from the workflow, aided it with computational modeling. And then what was really nice is that we conducted automation to property screening as well, not just computationally. So we conducted a host guest assay on our different creative materials to see binding properties. So I hope in a very whistle-stop tour, I showed you how we can streamline the automated discovery of POCs. We explored the effect of internal effects, so precursor design on the outcome of reactions. We can create a machine readable experimental computational database all through our automated workflow, extended this to our other materials, automated property screening, and now we can utilize all of this data towards other data-driven methodologies for different optimization tasks. Yeah, thank you to my 2 wonderful supervisors, both the groups, everyone on the screen, and all my funders.